coding a text-to-speech model from scratch. I trained it on PyTorch on an A100 GPU for few hours. And here is the breakdown of the same. Hey, this is Mayank Pratap Singh. Speech to text is a task of converting spoken audio into written text. It is used in voice assistant, generating subtitles on YouTube, and more. There are many approaches and architectures for speech to text, such as deep speech, wave-to-vec, whisper, transformers, etc. In this project, I have trained a transformer STT from scratch. I have a long list of audio models, both speech to text, text to speech, and audio to audio models. And in the future, I am going to code the rest of the architectures and train it from scratch. So if you want to stay updated on the audio deep learning track, you can follow me. Also, please repost this post so that more people can learn about it. Right now, I am on my phone. I have opened a voice recorder app. Click on record and you can see the waveforms of whatever I am speaking. These are known as audio waveforms. It is a discrete representation of audio in digital devices. The x-axis is time and the y-axis is amplitude, which represents air pressure changes captured by the microphone. Here I have an audio file. When we zoom in, each tiny point you can see is known as a sample. Combining multiple samples per second gives us a sampling rate, which is measured in hertz. For example, 16,000 hertz means 16,000 amplitude values per second. So audio is basically stored as a 1D array of floating point numbers, and this array is saved inside a .wav file. If you want to read more about audio deep learning and the fundamentals of audio, you can check out my blog. For the tokenizer, I have used two types. The first one was byte pair encoding and the second one was character tokenizer. I have made a very detailed video about BPE, so you can refer that for the same. Let's focus on the character tokenizer. So we have 26 alphabets, a blank token, and an apostrophe. The vocab ID ranges from 1 to 28. Basically, it covers A, B, C, D, the blank token, and so on. The dataset that I am going to train it on is LJ speech dataset, which has 13,000 clips of audio and text transcript. The average clip duration is 7 seconds. Let's take a sample audio.
The examination and testimony of the experts enabled the commission to conclude that 5 shots may have been fired.
These are the audio waveforms, which are just an array of numbers, and this is the transcript of the audio. Now, we have to pass this audio into the self-attention mechanism. As you know, the model will take audio as the input and spit out the text as the output. This 7-second audio at 16,000 samples per second results in approx 112,000 samples. So the input sequence is basically 112,000 numbers. But here is a problem. The architecture is transformers and attention scales quadratically. So let's take an example. If I have the sentence, hey, this at Mayank, which is 4 tokens, the attention mechanism create a 4x4 grid, that is 16 values, which is perfectly fine. Let's take another example. Here is a paragraph. The token count is 105. The attention for this would be 105 into 105 grid, which is about 11,000 values. Still manageable? But what about 112,000 values for our audio input sequence? This is huge, as you can see. To fix this, we are going to downsample the audio using a conv-net. By using this, it will reduce to approx 2000 to 3000 for this specific audio. As you know, attention can process 2000 values much more efficiently than 112,000 values. Next, we will pass this into the transformer architecture. I'm not going into details of that because I have made a very detailed breakdown of the transformers and also train a BERT model from scratch on my blog, so you can refer that. Also, I have made a blog about this project as well. So if you want to go into details of how to build this, you can read that as well on my blog. So after the input has been processed by the transformer, it passes to the RVQ. RVQ stands for Residual Vector Quantization. Before implementing this, I have implemented the standard vector quantization, VQ-VAE, and then the RVQ. The concept is that we have a codebook, and the task is to map our input to the closest similar embedding in the codebook. So vanilla vector quantization has higher error rates, but residual vector quantization uses multiple codebooks, and each recursive codebook minimizes the error further down the line. The difference between the input and the code is known as residual. We quantize this residual again using the next codebook, repeating this multiple times to capture as many details as possible. So the overall architecture looks like this. Now let's talk about the loss. The overall loss is a combination of the CTC loss and the vector quantizer loss. Let's focus on the CTC loss. In audio processing, there's a massive mismatch in the sequence length. You might have 16,000 audio samples representing just few text characters. There is no one-to-one mapping between the sound waves and the letter. CTC fixes this alignment problem, allowing model to learn temporal classification without explicit timing labels. This mechanism is the foundation of major ASR architectures like Deep Speech 2 and Wave-to-Wake. I will make a detailed post about that as well in the future. Okay, now everything has been assembled. I'm on RunPod right now, so let's launch a A100 GPU. After that, I'm cloning my Git repo to move the code to the pod server. You can also check the configs and change them according to your use cases. Maybe you want to use a different datasets, or maybe you want to use a different tokenizer, batch size, etc. Right now, I have downloaded the LJ speech dataset and moved it to my pod. Next, I'm going to create a virtual environment and install all the packages. Now the setup has been completed. If you want to start the training, you have to just run the main.py script. So after running it for 3 hours, I haven't got any good results. I was kind of like curious what went wrong. Was there a bug in the code? I couldn't find any. After trying multiple things, I have asked Abhishek, who has implemented a transformer STT in the past. He told me that it is kind of like tricky to train these models, and obviously it requires a lot of compute. Also, if you look at this plot, you will realize that a basic transformer STT is kind of old. There are many new techniques, and it doesn't make any sense to throw expensive compute on an old architecture. So the obvious answer was to reduce the dataset. I used only 200 audio clips for training, and it started giving some good results after 2 hours. As you can see, this is not a production-ready speech-to-text model. Technically, the model is overfitted on the 200 audio clips, which is why it is able to generate the results. That makes complete sense, since it is just a toy STT model for learning purposes. So, yep, that's it for this project. The code, the blogs, etc. are all there on my GitHub, and all the links are in the caption. Beyond this, I have implemented 2 different text-to-speech architectures as well. I trained them for 24 hours on an A100 GPU and got decent results. More about that in the future video post. Please repost this post and share it with all your friends so that more people can discover this track.